It is time. Hello.
Yeah. Hey, Luca. What's
Hey,
up?
Thomas. Yeah, what's up? What's up? I've been fighting with a messy code base that we don't own, but we have to deal with all day. It's weird. People get very creative with ML apparently, and making sure everything is kosher is not one of the things that people like the most. So we're trying to fight the good fight here
Right.
and give people better ways of acquiring things and transforming things. Otherwise it's like miserable. I spent hours trying to reconcile a situation. So anyway, that's my day. How about
Yeah.
you, Dan?
Yeah. I had a great week, and not that much going on. Just November, foggy days, stuff like
Oh
that.
yeah, yeah. Yeah, yeah,
Yeah. But
it's officially that season here too in northern Italy. It got cold, so we're preparing for a nice winter season. I'm all for it. All
yeah.
right,
So
so
one
yeah, yeah,
of
go
my,
ahead.
I'm not a big crime novel reader, but one of my favorites is the Le Voyageur de la Toussaint from
Aha,
George Simenon. Uh, but yeah, it
yeah,
starts
I love
in very
Simenon.
foggy La Rochelle and it stays like very foggy throughout the
Yeah,
story, basically. But yeah, so
yeah,
the
yeah.
other thing,
Anyway,
the other thing I thought about is that it would be neat if we like could take a look at other models that aren't like LitGPT, and
yeah,
so which other models do we know?
yeah. I don't know. In Llama Land, what is the implementation that everybody seems to run one way or the other? I think it starts with a H and ends with a E. Hugging
Oh, yeah,
face.
there we are.
There
So,
we are.
I mean, we
Yeah.
already had Llama 3.2 1 billion a couple of times on here. Um, and so let's use that too, but let's go with transformers this time, right? So,
So, yeah, what is the challenge here? Like, what changes from LibGPT, right? The two libraries are very different in nature,
yeah,
and not putting any blame anywhere. Like, to be clear, it's all great open source, but LibGPT tries to be minimalistic about the way it does things. So you open a file, you have your code in there, blah blah blah. Transformers tries to have everything in there, like all the models and so on, tries to minimize duplicated code. That means that you have a hierarchy. You have dictionaries going around left and right to represent complex data structures, just not just tensors. You have dictionaries because different models expect different things, and so they stuck all these different things into dictionaries, as I said. And so, Thunder being able through its own interpreter .py to handle all this complexity is quite an achievement if we make it. So we'll see what
yeah.
comes out of that.
So, I mean, one thing it doesn't completely do, and sometimes they don't use dictionaries, but use classes instead, like
Hmm.
result classes, and we're not fully covering those, unfortunately, and we'll see that. But let's just get started, right?
Yep,
So
yep.
transformers, and because we want llama, I'll just import the right thing, right? So import transformers models llama, and I think llama. Oh, from transformers llama import llama for causal 11, right?
Yep.
Because that's kind of the vanilla thing. So let's get a model. So with storage device, and I'm putting it on CUDA immediately just for ease here. And of course, if you're doing this in Studios, be sure to select the GPU. My favorite one is the L40S here.
Yep.
Because it has like more VRAM than any GPU I have on my own.
Yep.
Okay, so the model is Llama for causal LLM. And we can initialize it from pre-trained to and now I need to get the really right name here, but it's here, it's up here in
the right casing
title, right?
Oh yeah,
Meta Llama the right
Llama.
231B. And
Nice.
so because I'm a bit lazy, I'm just casting it to bfloat 16 here. And we want to do inference. So requires grad. People sometimes ask me whether, well, yeah, for models you don't have a choice, but for tensors, there's this method. And there's also, you could assign the property, but because I often misspell things, I'm always happier with the method, because that will error when I misspell things.
Yeah, that's a good point.
So what's going on? Yeah, all checkpoint weights were used. It's a bit more verbose than I would have needed, but yeah, good thing. So
Awesome.
we have the model here. We can look at it. It's a transformer with 16 blocks, and yeah, just this thing. And then, of course, we want to send some data to it. And so this kind of needs a bit of cheating. I prepared this, and so I need a number of things. So I have like cache positions, which is what we call usually the
Indices, right?
the indices. So it's a range on the CUDA device, and we have and I shouldn't forget the columns. We have the input IDs, which are just some tokens, right? Usually you would instantiate the tokenizer. We're not going to do that, but so the typical thing will be that you have a beginning of sequence thing, and then just some random tokens, right? And I just copied it from.
What did you write?
You can code it, and then you'll and we want the batch dimension to this, so let's have that. And it should also be device CUDA. And we need an attention mask. And now this is something where it differs a bit. The attention mask in LitGPT is always like a matrix. But so here there's a somewhat simpler one. We have a batch dimension, and then we have like the input positions, and the D type should be torch dot int64, and the device should be CUDA again.
Yeah, so the attention mask is derived from this specification, essentially.
Yeah. So the other thing is we don't pass the input embeds directly, so this will be none. We will have the KV cache. And here's the thing, we can't use the KV cache like directly. So we're using the dictionary version of it. But this will change. So it is one of my tasks in Thunder to actually fix that. Okay, so these are arguments, and we can check that we can run this through it if we call the model. Everything good, right? It's a somewhat.
Nice.
So here you can see that it's like the return class, causal LLM with pass. But yeah. Okay, so the
Nice.
JIT model, import Thunder, and the JIT model is Thunder JIT model. And now we want to call it. Yeah, let's do it. Let's call it for the first time here. And I'm just going to call it just the same. And we can imagine whether it works or not.
Well, yes, like the experience we expect is that something might be wonky there. Um,
Yeah.
And this is what recipes are for, right? So that you can stick all the particular things. And so maybe at the end of this like series of episodes on Hugging Face Llama, will come out with recipes that can incorporate whatever we learn here. So
Yeah.
let's see. It's thinking.
Yeah, I think it takes about a minute or so.
Yep.
But yeah.
The ultimate goal is to see if the vanilla Hugging Face transformer, llama transformer model using Eager is going to be slower, faster than ours. Hopefully
Oh, it
slower.
worked. Okay.
Oh, wow.
It
Okay.
did work, but I cheated. And unfortunately, I have to restart the kernel and run all the cells.
Why is that? Can you
Yeah,
reveal the
obviously,
trick?
I played a bit with it before, and so it was like the
Yeah. You already registered stuff. And
yeah.
so, yeah, the tell was that he didn't barf on with Tor's device before. So you must have had
Yeah,
imported something.
yeah, but I fooled you for the moment, right?
Yeah. Yeah.
But yeah, the numbers would have given it away too, right? The
Yeah.
execution numbers here. But yeah, so the not so good news is that now it will likely not work as smoothly.
Yep.
Uh, but I can look surprised nonetheless.
Yeah, right. Well, this is real life.
Yeah.
So,
So
like, if we support Hugging Face, like Llama, will it be probable that we also support other models of the same family from Hugging Face?
yeah, so that's the flip side. And so Hugging Face, obviously, they also have great velocity, and so you always have this when you develop these things. I mean, we also have this when we do Thunder or one of the other things. You always have to have a. Oh, now it works too. Okay.
That's interesting. All right.
Yeah, we fixed something somewhere. Okay, so I will tell you what's happening here. Um, I upgraded the version of Thunder like to the newest and fanciest. And if you want to try this at home or on your own Lightning Studio, you need to upgrade PyTorch to 251 and also NVFuser they're not like sitting on their hands. They're also improving NVFuser. And so you also want to have a new version of NVFuser. And I installed these. And one of the changes we did in Thunder that we now automatically say that it is a compiler when things query whether they're in a compiler, and apparently that is enough to get
Where
the
is the is compiler? Where? Yeah, let's explain this a little bit more, right? So
so you
Hugging
have the
Face, yeah, Hugging
torch.
Face went through the exercise of supporting Torch Compile. And
Right,
so by default, Torch Compile probably broke in a number of places with Hugging Face. And
right.
so Hugging Face inserted some clauses like, is it compiling or not, to change some of their code paths to be compiler friendly. And now we can actually piggyback on that same thing and take all the paths that are gentle to Torch Compile to also be gentle for us. That's the like very high level thing. So where is the flag there?
Well, so we can look at this. So we have this torch compiler is compiling
Mm-hmm.
function, and if you call it like this, it will return false.
Yep.
If we print it in a function, right? So obviously, if I call this, it will be false too. If I call that with torch compile fn, it will be true. And if I use thunderjit fn, it will also be true. And we achieve this by doing a look aside on this function. And so this is one part, but there's another part. And if I reinstantiate the model and I comment out this one, and now it will fail. And so there are two things. This is the is compiling, and one thing that compilers generally, deep learning compilers generally don't like is data dependent control flow. So one of the typical data dependent control flow things is that you check whether your inputs are all legit. So for example, that you don't have like invalid tokens passed into the model. Um,
Mm-hmm.
and Hugging Face does some of these checks, and that's very useful because sometimes users will pass in invalid things, and it might do anything between returning bogus results and crashing your model. And in PyTorch, there has always been like this also the idea: should we error on this or should we not? Because if you're in a CUDA kernel and you detect it there, then basically the only mechanism to error is to have a device assert, and that will
Mm-hmm.
not like work.
Be nice
So
at the very least. Yeah.
it's still working. I thought that I had something where there is a on the fly initialization of uh, of the uh, of the loss function, but apparently when you instant, and the difference was that I previously didn't instantiate it from the pre-trained model, but from the
Auto.
configuration itself. If you do that, you need another look aside, because in the first run, when it's not set up, uh, 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 the model itself will, during the forward, it will detect which loss function you want, and it will set up the loss function. And that runs into funny things, because it uses the Python regular expression module, and there are bits that we don't support in that, through the Thunder interpreter. And so I did make a look aside for this loss function, but apparently we don't need it. So let's jump right into more fun things than debugging compiler errors, right? So of course, we can do print the last traces, right? But one thing we can try is, did it get faster? So
Exactly. Well,
as,
let's see the vanilla one.
first the vanilla one. And so as usual, we need to add a torch CUDA synchronize in order to get proper values from timeit. And so we can have that, and then we can compare it to the thunderized version. And yeah, 13 milliseconds we have to beat. No, we're
And
looking,
then, yeah,
and we're
it's
slower.
slower. Yeah,
That's not good. What do we do if we're
absolutely
too
not.
slow? Obviously, we're going to profile it, right? So
Yeah,
we already saw how this works. So with Torch Profile Profiler, and I'll directly use with stack true, because that's a good thing. And we can profile the eager thing, and then just run the model. And then I will do a funny thing from from the rehearsal. I will take, or well, maybe we just print the key averages, right? So prof eager dot key averages
yeah,
dot table. Okay, and so we see that the self CPU time is 17 milliseconds. The self CUDA time total is 5 milliseconds, which is something you have to take apart here. We're spending 17 milliseconds in the thing, and only 5 of them are on our GPU. So something is up here, right? And if we
yeah.
look at the Thunder model, we see that it's similar, right? I mean, we
Yeah.
have 17.7 milliseconds here, and the CUDA time total is just 4. So we would be faster if it's just the CUDA time. The kernels are faster, but the overhead is larger.
Yeah, it's interesting that you also see that if you buy a better GPU here, it's gonna be helping you to a point, right? Pretty not that much. So, spending
Yeah,
more money here is not good. Spending more time on it, maybe yes. So, yeah.
yeah.
So how do we get out of it? Oh, first of all, what could be the reasons why Thunder is not able to cut that CPU time?
Yeah, so typically what happens is Thunder compiles the program into a program that does a series of function invocations, and these functions then process the thing. And so one of the things is that we dispatch to various backends, and apparently, like, these backend functions don't manage to saturate the GPU, which means that there are too many separate kernels, and also they're not launched quickly enough. And
Yeah.
we can do this, we can look at this a bit by using the Chrome developer tools. And we can grab Thunder trace here, which we get from export trace. And this will give us, yeah, I needed to upgrade the Chrome, and now the thing is not very well configured
Yeah.
in terms of screen layout, unfortunately. So
Yeah. So ideally, while you tinker with the layout, ideally we would want a diffuser or whoever is at the bottom to fuse as many things as possible. For some reason, this is not happening. And we'll look into that probably in the next episode. But there are things we can do to not suffer so much from what you're showing right now.
Right. And
Which
so what?
is, can you guide us through what we're seeing?
Yeah. So here on the top, we're having the Python bits or the CPU bits more generally. So this is the Python computation function, the Thunder computation function, which is the thing that takes the time. And then we have invocations of torch compile because we use torch compile as an executor. Here we have the scale.product attention, which has a special executor here. And here's a call to the nvfuser executor. And there are many of them. And some of them, like this one here, this is a fairly large bit. But then what happens is that, well, here you have matmults, which make good use of the GPU for a short bit of time, right? For 50 milliseconds, microseconds. You have many things here where there's 1 microsecond of kernel running in 100 microseconds, right? Or even more, like between 12
Yeah, it's
and
very, very sparse. Yeah,
you
very
only
sparse
have
utilization.
very sparse.
Yeah.
And this is the fault, basically. And so one thing here, and note that it's not just like Python overhead, but here we are in the C++, and the C++ still has 60 milliseconds. I mean, the Python has 21, but still 60 milliseconds is too long to like run 1 microsecond of a kernel, right?
Yeah, for sure. Yeah, so
So
we'll dig more into that. There may be tweaks that we need to do, but there's a way to get out of this situation.
right. And so let's get back to this. And so NVIDIA is, of course, keenly aware of the problem. And one of the things they did is they offer a little thing that traces through all the CUDA invocations and then allows you to run this really fast. And this is called CUDA graphs. And so we in Thunder we can use it pretty easily. Of course, PyTorch also has support for it. But so what we can do here is we can use Thunder transforms. It's implemented as a transform. Thunder transforms CUDA graph import CUDA graph transform. And if we have here as a transform the CUDA graph transform, and I need to instantiate it, we can run it again, and then we can see what happens. So what happens here when we use the CUDA graph is that all the bits that we saw at the top part, they are replaced basically by something that has already all the kernel parameters set up, and it's just running the launch that kernel thing on the CPU. And so you maximize really how fast you launch the kernels because all the setup, like CUDA kernels get the parameters in constant memory, which is a part of the VRAM that is cached, and that's why it needs to be constant. And all this memory is already set up, so you don't need to copy it to there. And so they can launch these kernels from the CPU really, really quickly. And so this should make it a lot faster. And if we run our timings, we see exactly that. And now we're
So
5
to apply CUDA graphs, we just had to add that in the transform. And so basically, it will take the trace and do something with the trace, which is a Python code. So we're structuring the trace in such a way that it can also acquire everything, all the traces as a CUDA graph. Okay, great.
And so we see that we like get very, very close to the like raw runtime, right? We
Oh
have
yeah.
raw runtime of 417, and so we have less than 1 millisecond overhead here, or approximately 1 millisecond of overhead here.
Yeah, that's pretty amazing.
Some of that will be also synchronized, but yeah. So
Yeah, yeah.
that's quite a powerful thing. You have to watch
Yep.
a bit because you have to watch out a bit because what I said about all the parameters being set up, that has implications that you, for example, need to have one thing, you need to launch all the same kernels with the same setup, like you want to have the same tensor sizes, and you also want to have the same tensor addresses. So in the
Hmm.
background, there's PyTorch allocating these intermediate tensors and reserving that space for the CUDA graph. And you have to watch out a bit that there's nothing funny happening. It can happen that, like, for example, we had kernels in our internal testing, like when we used an old version of one of the libraries, they didn't have support for CUDA streams, and then the recording didn't work. And so
Hmm.
that was a bad deal. But in general, this is a very powerful mechanism, and for our experimentation, we also and our optimizations, we also like optimize a llama type model
Yeah.
to work with this. So
So better than this could be fusing more, because it looks to me that we're not fusing a lot, right, compared to um, what we were doing in LGPT. So we will need to maybe look a bit more
yeah, I mean,
into that.
essentially the sequence, if we open the sequence again, uh, bear with me, more tools, developer tools. Uh,
Oh, can we actually create a trace for the CUDA graph just to see the effect of it?
oh yeah, we certainly
That
can.
would be very nice, because we saw all this time, all these little bars, we will see them packed together, right? So it's great. But as Thomas was saying, um, the the point there is that everything needs to be absolutely static. It cannot change, which we are basically doing anyway, because with Thunder we don't support dynamic shapes. So, for example, if you get with a sequence of different length, and you depend on the length of the sequence or a different bed size, you would need to have different traces, and so that or just retrace, which takes time. And so this is one of the things you need to watch out with compilers in general. Torch compiler has more support for dynamic shapes. JAX has no support for dynamic shapes, and we have no support for dynamic shapes. This may change in the future, but for now, this is what it is. So, so in this sense, CUDA graphs are not hurting too much from that point of
Right.
view. And then if you run them on kernels that are developed with support, like that comes out of NVIDIA libraries and so on, they generally work
Yeah. So
with CUDA graph.
now we have here the Thunder module. It gets called, and where does it call the? And here it just says call CUDA graph, right?
Aha. Yeah.
This is where the thing happens, and actually we
Yeah.
spent quite a bit of time in the prologue,
Mm-hmm.
which is something that you could also look at optimizing or even leaving out if you know that
Yep.
all the checks that
Well,
prologue does are okay. And then
right.
once we have the thing, we see here that the kernels are much more densely packed. Let me zoom
Yep.
into this a bit. Um, Basically, you see here Cutlass, and you see that there's the gem type operations chained, and then there's like small kernels in between, and it's the exact same kernels because we just like put them in a CUDA graph,
Yep.
same program. But they are now launched like without space in between, right? There's like tiny little gaps in between. I'm not sure how. Yeah, I don't think I can like zoom
Zoom
in
more.
fairly far. Uh,
Yeah.
but no, this is not the right thing. But so, but you can see that like there's not that much time in between those, and so it would be cool to just have a sequence like you have uh, uh, kernels that do the attention. Maybe it's more multiple of them if you split the attention by something, and then you
Yep.
have some pointwise stuff, a matmul, and always one kernel between matmul and self attention. Uh,
Yep. Because everything fuses together.
of these
Yeah.
three, like you have uh, uh, always like here you have matmul, and this probably is like the nonlinearity, right? There's fused here by NVFuser. This looks pretty good. Here you have a bunch of small kernels
Yeah, you
with
have a 810
probably,
one too. Yeah.
probably something like here's a vectorized element-wise kernel. You should probably be fusing that to something else, right? Um,
Yeah, exactly.
like
Unless MPFuser is falling back to that, right? So we don't know if that is hasn't been picked up because it was claimed by the eager executor, or if MPFuser is launching that because maybe it doesn't support something on its own. So this is very interesting to look into in the future. But we already got like crazy performance gains, like 60% or 70% performance gain by acquiring and then running with CUDA Graph, which is pretty amazing.
right,
Yep.
and awesome technology. Um,
Yep.
and so I think the thing that we see here is that usually, and I always say this, like people say that Python is slow, and of course there is something slow to Python, and we see that during the tracing, which is slower than CPython. We also do a bit more of tracking, but also like implementing a Python interpreter in Python will be slower than the raw deal. Um, but what we see here is that the make or break thing is not just Python, but it's also all the other administrative overhead, right? If you can
Yep.
cut that out and just throw the things at the GPU, then you'll be much, much faster. And so the crucial thing is to exactly evaluate when that is feasible and then do it properly.
Nice. All right. So first step done. We got great performance. We'll be digging more because what we want to get out of it is a series of recipes that people can just go and run with whatever implementation. And so
Right.
we'll be digging on why we're not getting the fusions and stuff like that. And then, of course, we're doing inference. Maybe we'll look into training at some point. So, yeah, I think
Yeah, and we should also look at like hopefully during the next few weeks, one of these days, we can show the advanced KV cache support because this here returns the KV cache as a dictionary, which is
yeah,
not the preferred way anymore. It works,
right.
but yeah, it can be nicer.
Yeah, yeah, for sure. And so anyway, we're layering in all this stuff. So yeah, I think we're done.
Right?
We're 40 minutes in, so
Yeah.
I guess
Right.
that was a great rundown, and we've come a long way. Like tracing through Hugging Face transformers is requires a lot of language support, a massive amount of language support.
Yeah.
So it's like you see a line there, but there's a lot of sweat behind it, and so it's super exciting to finally be here. And of course, we're also piggybacking the is compiling thing, but there's nothing we can do about it. Like data dependent control flow is something that none of us in the compiler world really, really supports. So that would be good. Although we could write Luca sites and stuff like that to kind of run around that, but up to a point. So apart from that, we're doing the whole thing, and we'll see next week what we find out about what's going on with all the small kernels
Yeah,
being launched.
a lot more of how the sausage is made, right?
Yeah, exactly. Like let's start ripping the peel of the sausage.
All right.
Nice.
Okay.
All right.
So have a good weekend and
Yeah, you too.
see you next week.
Yeah, see you
Bye.
next week. Bye bye. Thank you.